Hello and welcome to Specific's Active Buildings in Practice webinar. My name is Joanna Clarke. I'm an architect and design manager here at Specific, Swansea University, where I'm responsible for designing our active building projects and in assisting others in developing their own active building projects. The aim of this webinar is to give you a brief introduction to the world of active buildings. We hope you find it interesting and would encourage you to get in touch if you have any projects you would like to discuss with us. Topics we're going to cover today. The first thing is to explain what an active building is and how they fit into the current global and political context of climate change. I will then talk about our active building demonstrator case studies, and finally we'll introduce you to our active building toolkit for designers. So the definition of an active building is one that supports the energy network by integrating renewable energy technologies for heat, power and transport through use of energy storage and smart controls. This slide shows the United Nations Sustainable Development Goals that we have committed to achieving by 2030. We're already a year into what is termed the decade of action. There is a lot of work to do before 2030, particularly in terms of the built environment. In 2021, the UK hosts the 26th Conference of Parties, which will bring countries together to accelerate action towards the goals of the Paris Agreement and the United Nations Framework Convention on Climate Change. This brings to the fore the urgency to tackle climate change and the need for practical solutions to tackle this through the built environment, which is the focus for our work. The active building solution is primarily focused on reducing energy and on the UK's 2050 target for net zero. We also are tying into the Road to Zero strategy to decarbonise transport, which originally set out goals to end the sale of internal combustion engine cars and vans from 2040, but last year this was brought forward to 2030. And as we strive to decarbonise heat in buildings, which is one of the biggest challenges we face, no new gas boilers will be permitted in housing after 2025. This is to ensure that we meet the Climate Change Act goals, which were amended in 2019 to cut greenhouse gas emissions by 100% below 1990 levels by 2050. Many local authorities, developers and large estate owners have set their own targets to achieve net zero before 2050 as well. Our own university is aiming for 2040. In 2019, the UK construction industry declared a climate and biodiversity emergency, where they set clear aspirations for building designers, contractors and engineers to ensure the buildings we design and deliver for our clients respond to the climate emergency. Last time I checked, there were 1,098 signatories to the Architects Declare register. So how might active buildings help us to meet some of our targets? Well, to ensure a stable electricity supply as we move forward, as both heating and transport are decarbonised, we need flexible energy systems that combine storage and smart controls, enabling control of both import and export of energy to and from buildings to help balance the energy grid. And active buildings offer a solution to do this. There are 6 core principles for active buildings. The first 2 are concerned with reducing energy consumption in buildings. The second 2 focus on optimizing energy consumption by including energy generating technologies and energy storage. And the last 2 focus on the integration of buildings with the wider energy network, including use of electric vehicle charging to help balance supply and demand. We have developed a few new build demonstrator projects since 2014, and we also have a large industrial building which has been used as a test bed for new technology since 2011. Today, I'm just going to talk about the active classroom and the active office. Our first full-size building demonstrator was the active classroom, which we constructed in 2016. This was very experimental. It included a mix of pre-commercial technologies combined with more established technologies. For example, a transpired solar collector that you can see here, which is on our south elevation, generates warm air which is supplied to an air source heat pump and an MVHR unit. We have the first building integrated photovoltaic or PV roof installation for a Welsh company called BIPV Co, a new PV window developed by NSG, and novel electrical storage devices. Firstly, saltwater batteries that you can see here, and more recently, these have been replaced with flow batteries. We also trialed a new form of construction, which was steel-framed panels that fitted together, that were constructed off-site and brought to site to assemble into the building, and an electric underfloor heating system, which was developed and manufactured at Specific. The University of Bath is one of our academic partners, and they have a PhD student currently undertaking a detailed life cycle analysis of our buildings, which is a precursor to them developing a tool or method to enable a simple life cycle analysis to be carried out at the start of a project. These pie charts show the proportion of embodied carbon in different elements of the building and highlight the biggest main contributors to embodied carbon. For example, it's important not to underestimate the amount of embodied carbon in building services, which is often assumed to be low and is actually more difficult to measure due to a lack of available information. Looking at some of the high-level numbers he has got to so far, it's clear to see which elements have the biggest impacts in a building. And the figures show how low the operational carbon is in comparison to the embodied carbon, which is largely thanks to the use of renewables. Some of the challenges we've encountered so far are worth highlighting. So the time it takes to carry out a detailed life cycle analysis, it's quite a significant chunk of time and hence quite costly. The available information. So there is often limited information for building services, for mechanical and electrical equipment, and also for innovative technology. And also the level of information is not always available at early design stages. Another challenge is that as-built specifications often change from what was designed due to maybe availability of materials or technologies, or maybe finding a lower cost alternative. And there is a need to make assumptions where information is missing. But it's good to know that in terms of carbon, we achieved the 2020 target set out in the RIBA 2030 Climate Challenge, even though it was constructed in 2016, and embodied carbon wasn't one of our main design parameters at the time. In terms of energy consumption, we align with the 2030 targets, which is actually what we'd expect for one of our buildings. The second case study is the Active Office. In 2017, we were awarded funding from Innovate UK to construct a second building next to the Active Classroom. This time the building was 2 stories and had to demonstrate repeatability. So we used modular construction by a local company called Wernick, who are based just a few miles away from the university campus. The newest technology on this building is the combined solar thermal and PV system on the south elevation, which you can see here. This was developed by a UK company called Naked Energy and was their first installation on a vertical facade. We collect a lot of data from these buildings, and this image of our display screen, which is situated in the entrance foyer, shows how we are visualizing the data that we collect to building occupants and visitors. One of the key things we're doing in this building is controlling import and export of energy in relation to either energy prices or carbon intensity of the grid at any time. And to enable this, energy storage is essential, as well as smart controls. This slide just shows different ways we can visualize the data. So we can, for example, look at the environmental conditions in all of the rooms, which you can see here on this floor plan. And we have a lot of heat meters, which are used for fast fault detection. While our focus with the design of our building was on the technology integration and systems optimization, many of the design and construction decisions were made with embodied carbon in mind. For example, the inclusion of significant self-generation of electricity and heat, use of off-site construction and efficient design, and storage systems to provide flexibility in time of use for some of our significant energy loads. The design was very centered around reduced energy consumption And this in itself, of course, drives down in-use carbon reduction. During manufacture and construction, the significance of using off-site construction and local manufacture reduced the embodied carbons of the materials used, and surplus materials were donated to community groups through the Recipro Wales scheme. The vastly reduced site time and also added to the reduction in embodied carbon, especially around site works and significant use of local supply chains. In use, carbon intensity actually forms part of our control strategy. We monitor the intensity of the electricity grid and calculate the battery carbon intensity. And one of the control strategies is based on reducing overall carbon emissions in use, the detail and impact of which I will outline next. So there are two primary challenges when tackling carbon intensity in use. The first is energy use reduction. So using the extensive data available, we were able to clearly identify systems for energy reduction. Sometimes this was based on better control, set points, timing, or setback temperatures. Other times this involved modifying the systems to enable lower temperature heating while maintaining the heating power. On a rolling 365-day basis, these changes produced an 11.5% energy reduction in energy use, which is approximately 61 kilowatt hours per meter squared. I should say this was prior to lockdown in last March. We don't have more up-to-date figures because we've not really been using the building much in the last year. Secondly, understanding the relationship between energy and carbon intensity for the storage elements. So by considering the battery as a bucket into which you put energy and associated carbon during charge cycles, when you discharge the battery, you are able to calculate a gram per kilowatt hour over what can be a complex energy source mix of both solar PV and grid energy. This method takes into account the grid carbon intensity at the point of charge. Significant solar energy stored reduces the carbon intensity of the battery. Charging from the grid moves the battery intensity towards the grid value, usually increasing, as you can see in this example. To understand the actual carbon intensity in use of the building, we need to look at energy consumption and the source of that energy for each 30-minute interval. The graph on the right here shows a cumulative sum illustrating that currently we have achieved an 18% reduction in carbon emission for the first quarter of 2020, again, prior to lockdown. And we've identified further steps we can take to continue with energy reduction. For example, we anticipate a further megawatt hour of reduction by examining the lighting and the hot water generation in more detail. And not only that, but by taking more active control of the charge and discharge cycle, we can at any point in time compare the grid and battery carbon intensity and determine whether to charge or discharge the battery using a sliding scale. We're also working with one of our other partner projects called Sunrise, which is also led by Swansea University, to design active classroom buildings for rural villages in India. An active classroom building could provide massive support to these rural villages, which often have unreliable, unstable, and intermittent electricity supply. So self-generation is of real value here. So the first building demonstrator will be constructed later this year, probably starting around September time. So moving on to the toolkit. This is something we've recently developed to share our experience and learnings from designing, developing, and operating our own active buildings, and to aid the design of further active buildings. This consists of a suite of documents which are available on our website here. Well, some are available on the website here, while some are still under development. And I'm going to briefly run through some of these documents now. The first document is an active building code of conduct, which sets out clear expectations for an active building project and could potentially accompany contractual documents for an active building project. We have a short induction to active buildings, which provides a broad overview of specific and the active building approach. And we would suggest this is viewed by anyone embarking on an active building project. The Active Building Design Guide describes the key principles of an active building and provides key design considerations aligned to each principle. The glossary is meant as an accompaniment to the other documents within the toolkit. So it provides descriptions of all the acronyms, units of measurement, relevant policies, etc., all of which are referred to in the other documents, particularly the design guide. We've got a technology showcase document that gives examples of some of the technologies we've either used in our own active buildings or are aware that may enable the active building principles to be achieved. We'll probably be updating this regularly as and when we come across potentially suitable technologies. We've got a series of active building case studies, which we'll be adding to. The shed case study has been developed as part of our 10-year celebrations, and this gives an overview of the different demonstration projects we've developed at the shed over the years. We plan to add to these case studies with shorter case studies on particular aspects of each building. For example, thermography studies, battery system development, our resistive heating system, our optimization strategies, demand side response projects, and carbon reduction measures. We've collated all the questions we've been asked in previous seminars into one document where the questions have been grouped under headings such as costs, carbon, risk, retrofit, and others. We're currently developing a series of checklists to use at each of the RIBA plan of work stages of a project. And this is to assist the project design and delivery teams in making sure they've considered all aspects of an active building necessary at each of the stages. And we're developing this by trialing it on a current live project. So when that's ready, we'll be uploading that onto the website too. Other documents we're currently developing include monitoring specifications for different building types and an energy dashboard specification. Again, these will be uploaded when they're ready. I just wanted to mention here that researchers at the University of Bath are also developing an active building code, which will provide a way to rate an active building using a standardized approach, which is similar to other environmental assessment methods used for buildings. This is in its early stage of development, but there's a reference to their latest publication here, which provides more detail on the approach to this code. And that brings us to the end of the webinar, just leaving me to say thank you for listening, and please do get in touch if you have any queries.